Hi, welcome to Power Quality Lecture Series. Today we are going to see about how to quantify the voltage sag magnitude in radial system. In order to quantify, we need to first identify or draw the equivalent circuit or obtain the equivalent model. So here what we are considering is, for the simplicity purpose, we are assuming a voltage divider model for the single phase system. This voltage divider model, as you can see on the screen, is represented with two impedances, ZS and ZF. So this model is rather simplified and useful model to predict the properties of the sag, especially for the transmission system. The two impedances are ZS is the source impedance at the point of common contact, or you may also call point of common coupling, and ZF is the impedance between the point of common contact or common coupling and the fault, or at the instant of the movement of the fault. So you might just recollect back what is point of common contact. So the point of common contact or common coupling is the point from which both the fault and the load are fed. The voltage of the PCC and thus the voltage of the equipment terminal can be found by the equation, and which is nothing but the sag, and it can be given as ZF by ZS plus ZF into E. So this is a simple voltage division method that we have applied. So as you know, we always deal in per unit system. So the source voltage E can be assumed as 1 per unit, and then the sag equation will now be converted as in terms of only impedance, that is the voltage sag at point of common contact or common coupling is ZF by ZS plus ZF. So as I already said, the fault, any fault impedance has to be included in this feeder impedance. ZF is not the fault impedance, it is the feeder impedance. It is the feeder impedance and the fault impedance if any fault is occurred. Okay, let us name this equation as 4.9, and from this equation we can see that the sag becomes deeper for the electrical faults closer to the customer. So why we say this is just simple mathematical thing. As the ZF is decreasing or decreasing towards the zero, here the denominator is reducing and the sag or the total fraction will be increasing. So as the ZF becomes zero, then it will be only the voltage sag will be increasing, or you can say the sag is becoming deeper, or the more sag. The other name of the more sag is, we have seen, deep sag, deep. And the name for the lesser sag is called as shallow sag. So other case, for the smaller system, that means when ZS is becoming large, so you can say in two ways. This is when the same happens when the ZF is becoming zero, or when the ZF is reducing. And the other instant is because we are having a two impedance, this voltage sag will be closer or having a deep sag, either when ZF is decreasing or even when ZS is becoming much larger than larger. Okay, so both can happen. If the decrease in ZF and increase in ZS is in equal content or in a proportional way, then the sag will not be having any change. It will be normal. But as the ZF decreases much more, or the ZS increases in different proportion, the change in sag in the system will be more. Okay. The sag equation, what you have seen that ZF by ZS plus ZF is used to, whichever is used to calculate the sag as can also be used to calculate the sag magnitude as a function of distance. When I say that function of distance, it means as a function of distance to the fault. Okay. Therefore, what we can do is we can replace this feeder impedance in terms of the distance, or you can also call the length. That is by replacing ZF as Z into L, where Z is the impedance of the feeder per unit length and L is the distance between the fault and the PCC. And when we substitute this, what we can obtain as a resultant of this substitution or this replacement in terms of distance is, now the sag equation is in terms of distance, that is in terms of length, that is the feeder impedance is in terms of impedance into length by ZS plus ZL. Now what we have done by this substitution is we are trying to quantify the sag in terms of a distance. Okay, it's a very good thing that we can do here. So I'll just we can have a little bit of a case study here. The sag as a magnitude, the sag magnitude as a function of distance to the fault has been calculated for a typical 11 kV overhead lines, and this is what you can see here. Okay, so this is the case study what I'm showing to you. So these calculations are based on 150 square millimeters over the transmission line, and for the particular transmission line is used, and the fault levels are, as you can see, 750 MVA, 200 MVA, and 75 MVA. So what we can, what we are trying to exactly say here is, you can see here, there are three different sags from the case study what we have updated. This is for 75 MVA, this is for 200 MVA, and 750 MVA. You try to analyze this case study or the result of the data what were taken from the IEEE standards, and try to analyze and share your point. You try and you tell me what are the observations that you can draw out from this case study. This remember that this is the analysis which is done on 11 kV, 150 mm overhead transmission line for three different fault levels for 75 MVA, 200 MVA, and 750 MVA. Try to conclude or analyze this and tell me what you are able to draw from this. Yes, very good. This is the response what I expect. So what you can see is the fault level is used to calculate the source impedance at the PCC. Okay, so I'll just say the observations. Before that, I'll just give you the other data that you might be missing there. The fault level is used to calculate the source impedance at the PCC, the feeder impedance to calculate the impedance at the PCC and the fault. Okay, so it was assumed the source impedance is purely reactive, and thus the ZS is J 0.161 ohms for 75 MVA, and the impedance of 150 mm overhead transmission line is 0.117 plus J 0.315 ohms per kilometer. Yes, I'm giving you the other mathematical data like ZS and this ZF. Now you can still apply your mind because I've given you the ZS value and ZF feeder impedance value. Now, all the mathematical things are open for you. Just try to draw your observations of this for this graph for this data with the values of the ZS and ZF. Yes, right, very good. So the observation, the main important observation is the sag magnitude increases. That is, the sag becomes less severe for increasing distance to the fault and for increasing fault levels. I'll just take you back. You can see here as the statement what we are saying is, I'll just try to recollect you back what the observation you're trying to make it out. Sorry, I think. Yeah, you can see. So what observations, the main observation that you need to understand here is the sag magnitude is increasing. You just see on the curves. First one, the bottom one is 75 MVA, the middle one is 200 MVA, and the top one is 750 MVA. So the sag magnitude here, this is the magnitude here, okay. For 75, this is the magnitude, this is the magnitude. And so what is happening, the sag magnitude is increasing, okay. The sag magnitude is increasing for increasing distance, okay, and and for the increasing fault levels. And the fault level is increasing, it is increasing, this the fault level is increasing. Other thing is, this is the distance. As the distance is increasing, again you can see here the magnitude is increasing. So this here, you can conclude the two things here. As the level is increasing, the magnitude, the sag magnitude is increasing, and also along with it, as the distance is also increasing, the sag magnitude is increasing. So other thing what you can just you can try to observe here is when you, this is a 10 kilometers, distance is in kilometers, okay, this is 20, this is in 30. And compare here for all the different 10 kilometers, 20 kilometers, 30 kilometers, what you can observe is the fault at 10 kilometers distance are causing or may cause severe sag, because you can see it, this is the 10-kilometer point. This is the 10-kilometer point. So at this particular 10-kilometer point, yeah, this is the 10-kilometer point. At this particular 10-kilometer point, you can see here the sag is more, and you can call it as the sag is severe. So there is the reason why these are the types of these are the different types of observation that you need to draw from the case study. Let us also see now just whether will there be any effect of the cross-section area, because we have been seeing a transmission line where you have different types overhead transmission line, underground cables, whether this cross-section will also have an effect on this sag. My question to you guys, whether will there be an influence of cross-section? You're right. The overhead transmission lines or overhead lines have different cross sections, have different impedance, and the lines and the cable also have different impedance. That's the open thing. What do you know? And because this sag is depending on the impedance, the failure impedance or the fault impedance, which is combined, obviously we can conclude that the cross section will have obviously an effect on sag. It is thus to be expected that the cross section of the line or cable influences the sag magnitude as well. The same thing I'll show you here. I'll show you another case study between which will be comparing your overhead transmission line and all this, which you can easily try to understand here. So, what this plot, this upper one is for the overhead transmission line. Is the sag magnitude of the PCC as a function of distance between the fault and the PCC. This is for 11 kV. Is for 11 kV overhead lines with 3 different cross sections, 50, 150, and 300. Okay, the below one what you can see is for underground cables for the same 11 kV for 50, 150, and 300. Yes, you can see here, you can just try to observe and you can try to draw the conclusion from this. See, this is already indicated here. This is see how the way it is, how it is happening, how it is scattered here, and how it is there. Okay, so this is how you can understand. So a source impedance of 200 MVA has been used here. That's the data. Okay, the smaller the cross section, the higher the impedance of the feeder, and thus lower the voltage drop. That's the reason why you're able to see there. For overhead lines, the influence is rather small as the reactance dominates the impedance. Okay, that's the reason why you can see the overhead lines, it is having less impedance, less influence. Okay, for underground cable, the influence is much. Okay, if you want, I'll take it back to the uh, graph once again. For underground cables, the influence is much bigger. Again, for the different cross section, the same what you've seen. The inductance of the cable is significantly smaller than the overhead line. So the resistance has more influence on the impedance and thus the sag magnitude. I think now you are able to understand the reason why it is. Okay. Tomorrow we'll see in the next session, we'll see how this calculation for all different things. If you want, you can also have a do a case study. What are the impedance and different parameters that are used to calculate those. And next, we will see when the fault is behind the transformers, then how we can talk about the sag. Thank you.